All right, welcome to The Explainer. Today, we are tackling a question that seems so simple on the surface, but, well, it leads us down a rabbit hole into the deepest mysteries of the entire universe. It takes us from something you can hold in your hand all the way down to the very fabric of reality itself.
I mean, seriously, just stop and think about it for a second. The stars burning billions of miles away, the chair you're sitting on right now, the device you're watching this on. What are the fundamental, truly indivisible building blocks of all of it?
Okay, so here's how we're going to break this down. We're going to start by diving way deeper than the atom, where things get a little weird with something called a particle zoo. Then we'll see how scientists brought some order to that chaos with what's called the Standard Model, and how they found the cosmic glue that holds it all together. And finally, we'll peek beyond our current map to the huge mysteries that are still out there. All right, let's dive right in. To even begin to understand the fundamental, we've got to peel back the layers of reality. We're going to start with something familiar and just zoom in and then zoom in some more. So, picture this. We start with something you can see, right? Like your hand. Your hand is made of biological cells. If we zoom in on those, we find complex molecules, like water. And those molecules, they're just arrangements of atoms, which you might remember have a tiny, dense nucleus with electrons whizzing around. And deep inside that nucleus, we finally hit protons and neutrons. And for a really, really long time, scientists thought that was pretty much the end of the line. Protons, neutrons, and electrons, the final, fundamental Lego bricks of the universe. But it turns out, they were only about one-third right. The story goes way deeper for two of them. Well, it turns out protons and neutrons, they're not fundamental at all, not even close. They're actually made of even smaller, truly elementary particles called quarks. The electron, though, that one seems to be the real deal. As far as we can possibly tell, it's a truly fundamental, indivisible little point of stuff. And this is where things get really cool, because it's like a cosmic recipe book. A proton isn't just some solid little ball. It's a very specific combination of two up quarks and one down quark. But just swap one of those ups for a down, and poof, you get a totally different particle, a neutron. It's all in the recipe. So this whole quark thing, it was just the tip of the iceberg. It kind of opened the floodgates, and for a while there, in the mid-20th century, particle physics got really exciting and really, really messy. See, physicists built these absolutely enormous machines, right? Particle accelerators. And what they did was, well, they started smashing things together at mind-boggling speeds, close to the speed of light. They were basically recreating tiny little fireballs, mimicking the moments right after the Big Bang. And what came flying out of that wreckage was, well, it was a complete mess. A whole zoo of new, unexpected particles started showing up. There were heavier versions of the electron, ghostly particles that could pass through solid lead. The list just kept getting longer and longer, and that simple, clean picture of reality was just gone. I mean, it was pure chaos. Imagine taking apart a beautiful Swiss watch and just having a random pile of gears and springs on the table. How could any of this possibly fit together? Was there any underlying pattern to this particle zoo at all? But out of all that chaos, something incredible emerged. Physicists managed to build one of the most powerful and successful theories in the history of science, the Standard Model. The best way to wrap your head around the Standard Model is to think of it like the periodic table, but for everything. It took that whole chaotic zoo of random particles and organized them perfectly into a single, elegant chart that actually made sense. So here's the gist of it. The model puts all the matter particles, the actual stuff, into these three columns, or generations. Now look at generation 1, the up quark, the down quark, and the electron. That's it. With just those three, you can build every single atom in the universe. The other two generations, they're basically just heavier, unstable copies of the first one, weird particles that pop into existence for a fraction of a second and then disappear. Okay, so we've got the building blocks, the bricks of reality, but what holds them together, right? What's the cosmic glue that stops those quarks inside a proton from just flying apart? Well, that brings us to the other half of the model. And the Standard Model gives us a beautiful answer. It splits all particles into two main families. You have the fermions, those are the bricks we just talked about, and then you have the bosons. Think of them as the cosmic glue, or maybe like little messengers that carry the forces between all the matter particles. And check this out.
Each of the fundamental forces has its own special messenger particle, its own boson. The strong nuclear force is carried by the gluon. It literally glues quarks together. Electromagnetism, which is behind light and electricity, is carried by the photon. The weak nuclear force, which handles radioactive decay, has the W and Z bosons. But look closely. There's a big one missing, isn't there? Gravity. It just doesn't fit into the standard model.
And that brings us to the last piece of the puzzle, the celebrity of the particle world, the Higgs boson. It's tied to an invisible energy field that fills all of space. You can think of it like cosmic molasses. The more a particle has to drag itself through this Higgs field, the more mass it has. And that is why it was such a huge deal when they finally found it back in 2012 at CERN's Large Hadron Collider. The Higgs was the final missing puzzle piece. Finding it was this massive triumph, confirming decades of incredibly hard work. So the standard model is this incredible achievement, right? A total triumph. But it's not the whole story, not by a long shot. Our beautiful map of reality is actually missing most of the territory. See, for all its power, the model has these gigantic holes in it. Like we mentioned, it says absolutely nothing about gravity. And even worse, it has no explanation for the two biggest players in the entire cosmos: dark matter, the invisible stuff that holds entire galaxies together, and dark energy, the mysterious force that's pushing the universe apart faster and faster. And this, right here, is probably the most humbling fact in all of science. Everything we've talked about, all the quarks, all the leptons, all the bosons, this entire beautiful, triumphant theory only explains about 5% of the known universe. Just 5%. So that leaves us with this one absolutely mind-bending question. Our best, most complete, most tested map of reality is almost entirely blank. It means the quest to figure out what everything is made of, it's not just far from over. In so many ways, it feels like it's just getting started.